Alright guys, let's get started. I'm just going to run through all these problems on the board. If you have any questions, stop me at any time, ask whatever questions you need to ask, and we'll go from there. So the first question asks to write VR and VL into rectangular form. So what we could do, one of the first things we want to do is draw up our real and imaginary axis. So our x-axis is going to be the real axis, and the y is going to be the imaginary axis. So looking at VR, we have a value 1 at a 0 degree angle. So it's just going to be a horizontal with length of 1. So it's strictly real component right here, and this is V sub r. We also have V sub L, which is at 90 degrees, and it only is contained in the imaginary axis. So just visually, we can see that VR only has a real component, and V sub L only has an imaginary component. So if we want to put this into rectangular form, VR is going to be equal to 1 plus 0j. Coming back to here, our rectangular form is our real component plus j times our imaginary component. V sub L is going to be equal to 0 since there's no component along the x-axis or the real axis, and we have 1j. So this is going to be the rectangular form for both VR, V sub r, and V sub L. The second part of the question asks to put V, which is equal to VR plus VL. It wants us to put this in a rectangular form and polar form. The easiest way of doing this is just because we have our real and imaginary components of both V sub R and V sub L. We could literally just add this up, have V equal to our real components, which is just 1. 1 plus 0 is 1. And then do the same thing with our imaginary components, which will be 1. So this is the rectangular form of V. Now, using the equation over here to go from rectangular to polar form, the components that we need is our magnitude, which is A, and our phase, which is theta, or our angle, which is theta. So to find the magnitude A, we have magnitude A is equal to the square root of 1 squared, the real component squared, plus 1, which is the imaginary component squared. So this gives us the square root of 2 for our magnitude A. Alright, I'm getting close to the edge. Our theta then is equal to the inverse tangent of our imaginary component, which is 1j, so it's 1, over our real component, which is 1. This gives us a phase of 45 degrees. So the polar form of V is going to look like the square root of 2 times, or at an angle of 45 degrees. Or we can put it into this exponential form. I don't know if you went over this in class, but we can put it in an exponential form, which will look like this. Square root of 2 times e to the j, 45 degrees. So this is our rectangular form. This is the polar form. Any questions for this problem? Pretty straightforward. Alright, cool. The next problem we're doing is 5-4. It's similar. It's similar, except this is going to be -9. Does anyone need to copy this down? Everyone good? Alright. Alright, so for 5-4, the only difference to the circuit is we switched an inductor with a capacitor, which is not important right now. But the equations for this is going to be V sub R is equal to 1 at an angle of 0 degrees, and V sub L is equal to 1 at an angle of negative 90 degrees. So we'll go about this problem the same way as the previous problem. We can draw it out, again using our imaginary real axes. So V sub R, we can see is at 0 degrees, so it's with a length of 1, so it's only on the horizontal axis, the x-axis, which is just the real axis. So V sub R. Because this is negative 90, we'll go negative 90 from the origin. So it'll be down here. This is going to be our V sub L. So it's a little different than the previous problem. Instead of being at a length, it's still at a length of 1, magnitude 1, but it's down, so it's going to be a negative 1 when we write this in rectangular form. So V sub R is equal to only a real part, so it's 1 plus 0 times j. V sub L equals, there's no real component of V sub L, so it's 0 minus, because it's in the negative quadrant, negative 1j. So this is the rectangular form of both our V sub R component and V sub L component. The second part also asks to put V into rectangular and polar form. So we'll do it the same way as we did before. So V is equal to 1 minus 1 times j. Just by adding up our components, our real components of VR plus our real component of VL, and our real component, or our imaginary component of V sub R, and the imaginary component of V sub L. And this will give us our rectangular form. Now to go to the polar form, we do the same thing following these equations. So we're going from rectangular to polar. So we're going to use this to find our magnitude and this equation to find our angle. So the polar form, magnitude A is equal to the square root of 1 squared plus negative 1 squared, which will be positive and will give us a positive root 2 as our magnitude, the same magnitude as before. The angle is going to be found using the inverse tangent of the imaginary component, which is negative 1 over the real component, which is 1. This comes out to be negative 45 degrees. So now the polar form of our equation, the polar form of V is equal to the square root of 2 at an angle of negative 45 degrees, which is also equal to the square root of 2 times the exponential of negative j to the 45 degrees. So we're using the same method as before, and I think the most important thing to stress is our equations from going from polar to rectangular. So at least write these equations down. Know how it's set up. Know our axes, how the x-axis is the real component, the y-axis is the imaginary component. Have that, and that's pretty much all you need to solve the vast majority of these problems. Any questions about this one? No? Okay, so question 5.5 is the same setup as 5.4, except both the voltages are now going to have real and imaginary components. Alright, so because we have a positive angle at 9.5, we can draw V sub r on our axis as being something that looks like this. So it'll be at 18.44 degrees with a length of 9.5. So we could see that this contains both real and imaginary components, where the other ones just contained either a real component or an imaginary component. Now, VL, and this is V sub r, VL will be down something like that. 6, 3.16. So we could draw it visually, and we could visually see that both of these contain components of both the real and imaginary axis. So the first part asks to put V sub r from a polar form into a rectangular form. So to do this, we're going to use these equations right here, from polar to rectangular. So the rectangular form will get our magnitude A multiplied by the cosine of our angle plus the imaginary component J times A times the sine of theta. Sorry if I confuse you guys on that. It's A times the sine of theta. So V sub r is equal to 9.5 times the cosine of 18.44 degrees plus J times 9.5 times the sine of 18.44 degrees. So this comes out to be 9 plus 3J. Yeah, that looks right. 9 plus 3J for our V sub r. This is our rectangular component of V sub r. Now to find V sub L, we follow the same method, just with different values. Alright, so we have this. We just added our magnitude times cosine times our angle, the cosine of our angle, and this comes out to be 1 minus 3J. And this makes sense. We can do a sanity check by looking at our signs. Because V sub r is in the first quadrant, we know that we're going to have a real component in the imaginary axis and a positive imaginary component and a positive real component. So looking at this, we have both, knowing that it's in the first quadrant. Looking at the rectangular form of V sub L, we can see that we'll have a positive real component because it's the right side of the y-axis, but we'll have a negative imaginary component, and we have a negative imaginary component right here. Let's see that. So this is part A. This is the rectangular component. Now, if we're looking for V, which is a combination of V equals V sub R plus V sub L, we're adding the real components of V sub R and the real components of V sub L, and that's going to give us the real component of V. So if we just add these up, we get 10. And if we're adding up the imaginary, we're adding a 3j to a minus 3j, which is going to give us 0. So 0j. So this only contains a real component. And this is in rectangular form. It asks us to then go into polar form, which we do by finding, which we can actually visually see that this only contains a real component. So, and because there isn't an imaginary component, we know that this has to be lying on the x-axis, on just the real axis. So we know that it doesn't have an angle. The angle is 0. And if we wanted to find our magnitude, we would do 10 squared plus 0 squared, 0 squared being 0. We get 10. So our polar form will look like 10 at an angle of 0 degrees. Do you guys see how I got it from this without using that formula, knowing that there's not an imaginary component of it? Is there any questions on this? No? All right. I think the next problem is 5-7. Nope, 5-6. I lied. Still using the same circuit as this. So let's draw out this. Okay, so we're going to follow the same procedures as we did before with the other problems, using these formulas. So the first thing we're going to look at is find the rectangular form of V sub R, which is going to be 10 times the cosine of 60 degrees, plus j times 10 times the sine of 60 degrees, which is equal to which is equal to 5 plus 8.66J. We'll do the same thing to find the component BC. So we have it set up like this, our magnitude times the cosine of our angle to get the real component. This will be equal to 15 minus 8.66J. So these two equations give us our rectangular form of the VR component and the VC component. Now to find V, we add up these components. So 5 plus 15 is going to give us 20 as a real component, and this component, the imaginary component, is going to cancel like it did in the following question. Going to the polar form, we know if there's no imaginary component, it's going to lie only on the real axis, so we'll have an angle of 0. So V equal to 20 at an angle of 0 degrees. So right here we have our rectangular and our polar form. Any questions on this one? Nope. Move on to the next one. Alright, the next question is 5.9. I don't know if this was confusing because of the way that the circuit was drawn, but essentially you're following the same procedure. So this circuit is asking for current instead of voltage, and for circuits, for a double circuit or a double loop circuit, you're going to have two different currents. So the total current in this circuit is going to be equal to the current across the inductor, which we'll call I sub L, and the current across the resistor, which we'll call I sub R. So I will equal to I sub L plus I sub R. And we're given both of these components. So I sub R is equal to 86.6 at an angle of 30 degrees. I sub L equals 50 at an angle of negative 60 degrees. So we'll do the same thing as we did before. Erase this. So I sub R is equal to 86.6 times the cosine of 30 degrees plus J times 86.6 times the sine of 30 degrees. This is equal to 75 plus 43.3 J. So this is our rectangular component, a rectangular form of the I sub R component. Now we want to find I sub L. I do the same procedure. 50 times the cosine of negative 60 degrees plus J times 50 times the sine, negative 60 degrees. So I sub L comes out to 25 minus J times 43.3. Now, in order to find the total current, we're just going to add up the real components, the imaginary components. So we have 100, 75 plus 25, 100 minus, it's actually going to be plus 0, J. So that's going to cancel. So similar to the other ones, we only have a real component, so we're not going to have any angles. So the polar form of this is going to be equal to 100 and an angle of 0 degrees. Any questions on that one? Good? And the last question is 512, which is the same circuit setup, except this is a capacitor instead of an inductor. So I sub R is equal to 0.929 at an angle of negative 21.8 degrees. And our current across the capacitor is equal to 0.37 at an angle of 68.2 degrees. So the same method as before. If we want to just break up the IR component, this is equal to, according to this equation, 0.929 times the cosine of negative 21.8 degrees plus J times 0.929 times the sine at negative 21.8 degrees. So I sub R is equal to is equal to 0.863 minus J times 0.345. So this is the rectangular form of the I sub R component. Now we'll do the same for the current across the capacitor, the I sub C component. 0.37 times the cosine of 68.2 degrees plus J times 0.37 times the sine of 68.2 degrees. I sub C comes out to be 0.137 plus 0.344 J. So the next step asks to put it into an imaginary, or the total of the total current. So I sub C plus I sub R, which is just equal to the real components of I sub R plus the real component of I sub C, which equals 1 plus, they just rounded it. If we wanted to make, because of rounding, this is at 0.345, so these two terms will cancel, so this will give us 0j again. With the 0 imaginary component, we know that it has an angle of 0, so I is equal to 1 at an angle of 0. So I think the final question, or the final part, asks for the real and imaginary parts of I, which we kind of solved from the rectangular form. So this is our real component, and this is our imaginary component. So pretty much they were all the, what's up? Did you say anything? So pretty much all these problems used these equations right here to go from rectangular to polar form and give you an idea of the imaginary real.
So when there's 0j, that means there's no y component?
There's no y component.
So it has to be 0?
Yeah, it has to be 0 degrees. And the same would be for the real component. If there wasn't a real component, that would mean that our vector only exists on the imaginary axis, so it would have an angle of 90 degrees. And that would be the same if it was negative. So if we had something that looked like I equal to 0 minus 1j, then it would be negative 90 because it's on the negative j axis, on the imaginary axis. And that's just an easier way. You could still, if you use these equations, you'll still get the same answer, but just looking at it, that's the fastest way to go about it. Yeah, it's just a little shortcut. Is there any questions about this homework that you guys have? I think we were supposed to have somebody come in and show you guys SolidWorks, but it doesn't seem like they're here. So you guys can take the rest of the time to do Chapter 6 homework. If you have any more questions or any help with MATLAB, I'll come around and help you guys out.